Hello. This paper will be talking about mutually orthogonal Latin squares and balanced incomplete block designs and how to form them from Latin squares and their approaches. So as we know, BIBD refers to balanced incomplete block design, and Latin squares are n by n matrices which never have two or more same elements in the same row and same column. So this paper will talk about computing Latin squares and computing approaches to try and find the MOLS and BIBD by using the Latin squares and some extra functions. So the theorems and proofs are used from Introductory Combinatorics by Richard A. Brody. So this, as we can see, is an example of a Latin square. So we can see that no two elements are being repeated in the same row and same column. 0, 1, 2, 1, 2, 3, and so on. And we can notice one thing, that the elements are being shifted towards left, left, left. This goes left, comes over here, and at last we get the last element. You can see. And producing a Latin square is of order n by n square, because it's an n by n matrix. So we'll be using n by n complexity. For BIBD, suppose we have a Latin square and the order of it is V, and the same V can be used as the varieties for BIBD. So we can perform different techniques on the Latin square to derive the BIBD. B means number of blocks, B is the number of varieties, K is the subset taken from the varieties, so the size of each block, and R is the replication number, how many times an element is being repeated in each block. Not in each block, in all the blocks combined. And lambda is the number of each pair that is being repeated in all of the blocks. And it should be noted that all should be positive integers. And when we calculate, if r and or lambda comes out to be a negative value or a decimal value, if it's not a positive integer, that means it won't be a BIBD, it won't exist. So this will be the approach of finding MOLS and BIBD using the Latin square. So first we will be generating the initial Latin square, and if we are considering the mutually orthogonal Latin squares, then we'll go to the left side, we'll change the elements, and we'll use the formula as it's the theorem stated in the book by Brody, and we'll be forming all the n-1 Latin squares using the for loops in C++. And yeah, if the n is prime, then all the n-1 Latin squares formed will be mutually orthogonal. And if n is not prime, then we'll have to search for the mutually orthogonal, and it is marked red because it has not been worked upon. And then if we are looking for BIBD, we'll be just inputting 3 values, and we are taking only 3 values so that the error is minimized, and the other 2 values will be computed automatically. And elements will be selected from the Latin square, from which each row of BIBD or block, each block of BIBD will be formed. And then on it, we'll be applying 2 functions to check the, well, when we select the elements from this, we'll be getting incomplete block design, which won't be balanced. So to make it that, we'll have to check the number of pairs that are being repeated and number of each element that is being repeated in all of the blocks. And if the iteration reaches the max level or all the conditions are true, that means lambda and replication number it aren't exceeded, then BIPD will be formed. But still, it is a little bit error prone, as shown in the gray area. This and little bit for replication number also, it is a little error prone, so might give some wrong output. So for mutually orthogonal, we'll be using this function, and I'll write a prime number that is 5, and the first produced matrix is the initial Latin square, and the other 4 must be the mutually orthogonal Latin squares, as the number 5 is a prime number. Now for producing and displaying IBD, that is incomplete block design, might be or might not be balanced or approximate all BIBDs. So first we'll be inputting 3 values or initialize the program with 3 inputs. This is what I'll be doing, initializing with 3 inputs. And the inputs 3 is used to avoid errors. Other values, and we have the lemmas and theorems proof that has been mentioned before that we'll be using. With the help of those, we'll be using the Latin squares, the BIBD will be formed using that. And the approximated BIBD will be displayed, and a table for lambda pairs and a table for variety versus block. That will be table for the replication. Table for lambda pairs and table for replication. That is the repetition of each variety in block in all of the blocks that will be formed. So now looking at the tables, how will be the replication table formed? This is the approach for finding the replication number. So a B by V matrix will be formed, or a V by B. It has B columns and V rows. So using this, we'll be checking how many times a number is being repeated in each block, and in each block we'll mark what number is being repeated. So if the sum is more than the replication number, then that means the condition is not being met. Or it could be the number, the total sum of each row. Maybe we'll have to check that again. And this is the approach for finding the pairs. So varieties, and as we can see, these are all k choose 2 numbers of blocks or the spaces that will be formed. So each pair's sum will be noted, and if the sum is exceeded more than the condition or the lambda, then the code will reiterate and new BIBD block shall be formed. Now we will be testing with input 7, 7, and 3. So now we'll be running this program. Now we'll try this program for finding the BIPTs from Latin square. So as we can see a few numbers of where 2 rows are being repeated, and lambda should be 1, and we can see different numbers. And this is the table of how many pairs are being repeated, how many times. And this is the number of elements that are being repeated as was shown in the paper, in the report. The complexity for forming each of the Latin square will be n square, and forming n minus 1 Latin square will be n times more. So the total complexity will be n cubed. So performing operations on each row, the total complexity is going to be of order n cubed. For finding the total varieties, the number of varieties being repeated in all of the blocks, the complexity is going to be this.